Welcome to the physics video lecture, psci 168, video lecture 33. So I'm going to talk about solar energy some more and then send you guys out to do a little more research, kind of like we did last time. So let's start here with the idea of solar thermal, which was those power plants I wanted you guys to research, and I had told you how that works. I'll just put a little list of what we have so far. So first of all, we have the solar constant. And just by measuring water getting warm when it's out in the sun, we're able to determine that we have 1,340 watts per square meter. And realistically, down here on Earth at noon, it would be closer to 1,000. This is the full value if you're up above the Earth's atmosphere. You get everything, 1,340 watts per square meter. So good. After that, I started talking about the solar thermal power plant. And you guys have gone in, hopefully, and found some interesting images. And there's plenty out there, very interesting topic. What I want to bring up here before I move on is the question of the efficiency. So here's our solar thermal power plant. Once again, we've got this tower here, and it's got this cylinder on top. There we go. And the sunlight is reflected by a mirror. Here we'll make the sunlight red. This mirror tracks the sun and always reflects the sunlight onto the solar tower. And you got to see that there are just hundreds of them in one of those fields of mirrors in the solar thermal power plant. So the point of focusing all of that radiation from that enormous field to one point is to gather all of that energy and produce a very high temperature. Okay. So when you have a solar thermal power plant, you are really building this thing right here, our heat engine diagram. You know, your high temperature reservoir is obtained from this ultra high temperature molten salt or whatever they use up here. And you were going to look up the temperature values, they're quite high, okay? So that's what you get by concentrating it all in one point. Right, the low temperature reservoir is literally a reservoir of the molten salt that's at a lower temperature, and you're getting the work out. So yeah, you just have this heat source, which is the solar radiation, but when you send it into the solar thermal power plant operation, you're just back in this heat engine scheme. And of course, what was the efficiency? Efficiency 1 minus TH over T, other way around, pardon me. 1 minus TC divided by TH in Kelvin. And I didn't ask you last time, but if you research this, you should also be able to find some discussion of the Carnot efficiencies, or of the temperatures that it's operating between, and then you could actually come up with some estimate right there. So that's the important point. The reason that all the energy is gathered to one spot is to produce very high temperatures. If you don't need the ultra high temperatures, then you would just heat the water anywhere, right? You could just have a bunch of warm water, but you want ultra hot water or ultra hot some substance in order to run an efficient heat engine. So I'll just write here high temperature or high efficiency. And that's the reason for the collecting it there at one point. Okay. And when I say work here, W, that's just the output of a normal steam power plant. And we haven't gotten to electricity and magnetism. We're going to talk about generators, motors, transformers, the whole business in a couple of days. But I decided to concentrate on all these energy sources now. I have another really profound application of all of this. So our next topic, okay, we're going to consider this understood, I hope. Okay. Our next topic is the question, how powerful is the sun? How powerful is the sun? Question mark. In other words, we know it's big, we know it's far away, we know it's very hot, but can we actually put a number on it? If we're asking how powerful is the sun, then we're thinking how many watts, okay? How many watts? If that were a light bulb, what would its label say? 100 watts, 50 watts, what would the label say on a light bulb that is as powerful as the sun? And interestingly, we can answer this question with the material we've covered so far. A little bit of stuff I'm going to have to give you without proof, but you'll be surprised, we actually have this. So how powerful is the sun? The way to discuss that is with our solar constant. So here's the sun at the center of our solar system. And here is Earth. And as you know, Earth orbits the sun in a big, nearly circular orbit, close enough. So there's the Earth. And the power of the sun here at the Earth is 1,340 watts per square meter. So what we have to imagine is okay, I'll draw some rays here, okay? So the sun's energy is radiating in all directions. Earth is just picking up a tiny bit of it. So any square meter out here, 1,340 watts. How many square meters are surrounding the Earth at the distance of the Earth's radius? Imagine a sphere of the radius of our Earth-Sun orbit. Now I'm going to label this. We're going to call this distance here from the sun to the Earth R sub sun to Earth, R sub SE. That's the distance from the sun to the Earth in meters. Okay. So how many square meters on this gigantic sphere that is surrounding the sun? Okay. And I'm just going to write the formula and then explain it. So the power of the sun is the solar constant from up there times the area, right? If you take I times area is I times A, okay? Watts per meter squared times meter squared, okay? So solar constant times, I'm just going to write this, area of sphere of radius R ES. I'm calling it RSE, am I not? Okay, RSE. Surface area of this sphere here. So the power of the sun is equal to this I times, and now we just need the formula for the surface area of a sphere, which is 4 pi r squared and I'm going to do this for you, let's say next time, but leave room in your notes and actually consider this to be a homework assignment because it'll be fun. So what you're going to do is use this value up here, 1,340, okay, that's I equals 1,340 watts per square meter. That's for I. Let me write this so it's readable. So with I equals 1,340 watts per square meter, and R being distance from the sun to the earth in meters. So you could look that up. Okay. I'm going to do this because I have a couple other things in mind as well, but I think this is a good one for you guys to look up and find out for yourself. Okay. Okay, so this is going to be a very large number, and you're of course going to want to use your powers of 10. Okay. So when you get this expression, I'm just going to write here homework, calculate power of the sun, and express your answer in scientific notation. So some number times 10 to the so and so many, right? Powers of 10. Okay, calculate P sun and express in scientific notation. Because there are going to be a lot of zeros, let me tell you that. Okay. But, you know, the distance from the Earth to the sun, we may have talked about it early in the semester. I may have given you a whole chart of these values. If not, you got to look it up. It could be in your notes. The point is we figured out the shape and size of Earth, and the distance from the Earth to the sun is one of those geometric astronomical things. So it's not some great mystery. It's it's a quantity that astronomers and people can figure out. So that's all we have in here. The other thing we can literally get, right, solar constant by warming up water in our backyard. And those two ingredients tell us the power of the entire sun. As well as being a big number, there's another point I'm going to make. Okay, so that's the first part of what I want you guys to tackle. Power of the sun. In watts, in scientific notation, right? In watts, scientific notation. Okay, what's the second thing? Now the second thing here is the question of what kind of fuel is the sun burning? Okay. That's an awful lot of watts, and the energy has to come from somewhere. So after we figure out the power of the sun, we're going to answer a different question. Okay. Good. So that was next. That was power of the sun. Next here, how long would the sun continue burning? Okay. You know, if it's a candle, it gives off so many watts, and then it burns out and it's over with. So the question is, how long would the sun continue to shine or burn? Let's say it burns. How long will the solar fuel last? How about that? There's a way to talk about it. How long will the sun burn? And the thing is this, we have the formula power equals energy over time, or work over time. I'll go ahead and write energy divided by time. We did a similar thing when we were talking about the hydroelectric dam, how long it would take for the water to run out, that kind of thing. So we just solve for time. Time is equal to energy divided by power. Now, we just figured out the power of the sun right here. Okay, it's just some big number. But the question is, how much energy does the sun contain? And that we don't know. We're going to have to make a guess. At this stage of our discussion, we don't know it's that. The only energy source we know about besides gravitational energy for hydropower is the energy in fuel. So what we're going to do is assume that the sun is burning fuel. Burns fuel. Now I think it was the last lecture or the one prior to that where I figured out how much energy in fuel. Okay, how much energy per gram or per kilogram. And let's just go ahead and do that again because I don't memorize those numbers. We know we have 1 kilocalorie, 1 calorie per gram, and we have 10 to the third grams per kilogram, and we have 4,186 joules per calorie. So when we do you see we can cancel these calories, grams, we're left with joules per kilogram. And as I recall now, I rounded that up. So that's 5 times 10 to the third, approximately 5 times 10 to the 3, 4, 5, 6, 7. So 5 times 10 to the 7 joules per kilogram. So we're going to say fuel has 5 times 10 to the 7 joules per kilogram, and then we need to know how many kilograms in the sun. So what is the mass of the sun? So this is the formula we're going to use. And this is the energy density of fuel, and it's joules per kilogram, so we need how many kilograms, what is the mass of the sun? Okay. So, like this. So next, find the mass of the sun in kilograms. Of the sun in kilograms. Okay. And again, you can look this up. You can look in a book, look it up online. This is the one thing that I haven't really been able to prove to you, because we can't do everything in physics, although we're trying to do everything. Okay. So I'll tell you a little bit about the mass of the sun in kilograms in a moment. But just to put this problem together here, so then the energy, we're going to call it W. So the energy, because we like to use the letter W for work, it's going to be this energy density. I'm going to call it rho. I'm going to write this out in words for you. So it's going to be energy per kilogram times the number of kilograms. Okay. So this is your 5 times 10 to the 7. 5 times 10 to the 7 joules per kilogram. And this is your number of kilograms for the sun. And so this is going to give you some big number. And then the formula, I'm going to write here, finally, I'd like to have everything up on the board. I use this right here. So here's our, okay, I'm going to erase since I have this down. I need some room. Like I said, I'm going to do this next time. I want you guys to tackle it though, because because we have the skills now. Okay. So here's our formula. Time t is going to equal to the energy, which I'm calling capital W, and I'll say energy sub sun divided by power sub sun. Okay, time is the energy divided by power. But we're using standard units now, so we're using joules here and watts here, so these are seconds. In seconds, okay? These are joules, these are watts, so watts times seconds is joules, right? So these are seconds, and this is going to be a big number, and we want to convert the answer to years. So finally, convert your answer to years. Now that's easily done. 1 year, you'll just be dividing by a number. 1 year is equal to 365 days, 24 hours in a day, and 3,600 seconds in an hour. So this big number here, that'll be the number of seconds in a year. You divide this number by the number of seconds in a year, and you get the number of years. And the answer will surprise you. And the answer is small enough in years that we have to conclude unequivocally the sun does not burn fuel. Okay, but those are the things we know right now. We know the power of the sun simply by heating water out in the sun. We know the energy of fuel. We can claim to know all these things experimentally. We know that we can find the distance of the Earth to the sun by using some clever geometry. Ask the astronomers for some help, maybe. So the only thing missing here is how do you find the mass of the sun? It's actually not that far off from some of our work that we've done in physics this semester. The mass of the sun can be determined by Newton's law of gravity, which we dealt with. We did laws of free fall and gravity, so we've done some of that. But Newton's law of gravity tells us the mass of a central body if we know the period of the orbit. And we know the period of the orbit of our Earth around the sun. So that allows us to determine the mass of the sun. And for example, we know the period of the orbit of the moon around our Earth, and therefore we know the mass of the Earth. That kind of argument goes on. Let me go ahead and just put that in your notes for reference, just so, since I'm mentioning it. And then I'm going to send us on our way, because I think you'll find this very interesting. It's just I've laid out all these calculations, and of course I'm going to return to them, but I want you guys to have a try at it and look up these things. If you're like me, when you go look things like this up, you usually learn 10 more things just on the way, so it's time well spent. So yeah, I'm going to finish off with just a little note about how we know the mass of the sun. And I'll put a little technical stuff there. You can just put it in a box, or just put it on a page. Because that's the one missing thing. Everything else we've actually dealt with rigorously. How do we know the sun's mass? Okay. So Newton's law of gravity. So let's just do a top view. Here's the sun. Here's Earth's orbit around the sun. And that's our sun, Earth. Okay. So Newton's law tells us if we know the orbital period, the time it takes to go around, and the distance, we can figure out the mass of the central body. So I'll write here, using Newton's law of gravity I'd love to teach us all this stuff, but we can't do everything in one semester. Good. Using Newton's law of gravity, if we know our sun Earth, so that's the radius of the orbit, and t equals the period of the Earth's orbit, which we know is a year, and in fact we can express a year in seconds like this, equals the time period of orbit we can calculate the mass. And the formula that links those things, I don't have that off the top of my head. I think I do. It goes like this. T squared is equal to G M. Okay. I gotta do a quick little derivation. That's just the way it goes. So G squared yes. No, so the formula, good thing I did this. So the formula is T squared is equal to 4 pi squared over capital G, capital M times R cubed. This is a version of Kepler's third law. This we don't need. So I'm not asking you to calculate these, but this you can take to the bank. This is the time of the orbit. This is the radius of the orbit. This is the mass that we're looking for. And this is Newton's gravitational constant, universal gravitational constant. So the point is, it's well within our reach if you're a physics major, for instance, or you're a physicist, to know how come we know the mass of the central bodies of the sun. And that was just the missing thing in our calculation there, the number of kilograms of the sun. So when you look it up and you get a number, then you know it comes out of orbital mechanics and Newton's law of gravity. Yeah, well actually that's a good point, orbital mechanics. Okay. This was just for culture. I just wanted to make sure I didn't bring something out there that we look up. We're trying to understand everything we do. Okay, I'm going to leave it at that. So I hope you have some fun looking these things up. Try to calculate this. Again, we wanted the power of the sun, and then we wanted the time in seconds, how it would burn if it were burning fuel. And when you convert that time to years, you're going to realize that the Earth is a lot older than that. Okay, so, and that's going to lead us to, you could say, to the discovery of nuclear energy. Okay, because there's a whole other energy world that is not fuel, and I think this is a good way for us, in the context of this course, to introduce that. Good. So I'm going to leave it at that and talk to you guys next time.